thanks for inviting me. So yeah, today I'll talk about factors of low individual degree polynomials. And the talk is divided into 3 parts. In the beginning, I'll give an introduction about factoring and the model of computation that we'll use, arithmetic circuits that most of you know. And then in the second part of the talk, I'll talk about the main ideas that come into the proof. And I'll conclude with many open questions, because we still have many things that we don't know. So, okay, let's talk about factoring in real life. So factoring is a basic routine in many tasks, mostly known in computer science for fast decoding of Reed-Solomon codes, like unique decoding or list decoding, whatever you name it for Reed-Solomon. We use factoring for that. But in modern computer algebra, it's also used in many fundamental computations. For example, primary decompositions of ideals and computing Grosvenor bases, and etc. The good news is that can be done efficiently in randomized polynomial time. So we're happy about that. But since Avi is sitting here, then we have many things that we're concerned about. For example, de-randomization. We want to de-randomize this algorithm. We also want to study the parallel complexity of this problem. So far, the only algorithms we have are very sequential. And in general, we're also interested in understanding the structure of the factors, which I'll elaborate a little bit more in the next slide, or in a couple of slides. So arithmetic circuits, this is the model of computation that we'll be using. And here's a simple definition by picture. An arithmetic circuit is just a directed graph. So here, directed acyclic graph, and here all the edges are pointed upwards, where we have the leaves, and in the leaves we have either input variables or elements from a field, and in the top we have the output gate, which computes our polynomial. And each gate computes a polynomial in a very simple way, right? So for example, the plus gates compute the addition. So here, for example, we have x plus y, and so on and so forth. You can see how to compute. This model captures our notion of algebraic computation, because any algebraic computation that you make, we can just build a circuit that will compute the polynomial you're trying to compute. And there are 2 main measures that we're interested here. And the main measures are the size of the graph, which is the number of edges of the graph. And this measures the amount of computation that you're using to compute the polynomial. And you also have the depth, which is the length of the longest path from the root to leaf, which measures exactly the parallel complexity of your problem. Now, this model is interesting because many interesting polynomials have succinct representation in this model. So for example, the determinant, because we have Gaussian elimination, or you can compute the symmetric polynomials due to Ben-Or. That's a very simple circuit that computes the symmetric polynomials. And it's a major open question whether the permanent polynomial has a succinct representation in this model. Succinct is a small circuit that can be computed by a circuit of polynomial size. So whenever I say small in this talk, it should be small or succinct will be polynomial size in a certain representation. Yeah, but we won't be talking about this question today. Now, factorization. What is the definition of the problem? If I give you a circuit, or a small circuit or a small formula for a polynomial p of x, where p factors into a product g1 times g2 times gk, not necessarily distinct, the task is to output circuits computing g1, g2 up to gk. So in the 80s, Lenstra, and Lovász, and Kaltofen, they showed the following, that if p is computed by a small circuit, by a circuit of polynomial size, then so are all the factors g1, g2 up to gk. And moreover, Kaltofen gives a randomized algorithm to compute the factors. Okay? And this had fundamental consequences to circuit complexity and pseudo-randomness with the works of Kamenetz and Pagliazzo and Vir, Špilka, and Hodayov, and in coding theory with the list decoding of Sudan and Guruswamy Sudan, and in cryptography, the works of Chor and Rivest. So these 2 actually use just Lenstra, Lovász, and the top one uses actually Kaltofen.
So this is the randomized algorithm for factorization?
Right, yeah. Yeah.
No, it's 2 different ones. They are very different.
They're very different ones. Yeah, so this.
Lovász is deterministic,
Right, so the first one,
Works over any large.
right, yeah, Kaltofen works over any field, and this uses lattice, yeah. So now, what about depth? So what Kaltofen tells us is that factorization behaves nicely with respect to size. What he says is if you have a small circuit, then all the factors have small circuits, and moreover, you can find them. Now, what about depth? So he uses a technique that we'll see, Hansel lifting, which is very sequential. So we know nothing pretty much about depth. But more generally, we're interested in studying structure of factors. So the problem is the following. If I give a polynomial p in a circuit class C, let's say p is computed by a sparse polynomial. P does not have many monomials. Then which classes C star efficiently compute the factors of px? So C star could be C as well. For example, one question is, are factors of sparse polynomials also sparse? That is not known.
Well, I mean, definitely not true over finite fields.
Definitely not true over finite fields, exactly.
But you're not talking about finite fields.
Yeah, I'm mostly concerned about fields of characteristic 0 for now. Right, so Noga said that it's definitely not true over finite fields because you can just use Frobenius, right? And you have, let's say that I have x1 to the p plus x2 to the p plus xn to the p. So this is clearly sparse, and let's say our field is just fp. Then if you have this factors as x1 plus xn to the p minus 1 times x1 plus xn. So the factors of sparse polynomials are sparse is definitely not true when the characteristic of the field is not 0. Yes, but it's not known. It's not known if you can if it's false when the degree is less than the characteristic, or if the characteristic is 0. Yes.
Are they sparse?
So this is not sparse.
Yeah,
Because in dimension 1, you have all the, these are all the monomials.
You mean all factors, so that you can factor to sparse?
All factors, yeah, not the irreducible factors, right? I guess that's what your question was. Yeah, so if any factor can be, yeah.
Like more reasonable to ask about the irreducible.
But
I thought actually about one variable, x to the p minus 1.
right, so
P minus 1 minus 1 contains all the factors, basically.
right, yeah, but this does not scale to many variables. So the blow up there is quasi-polynomial. You have yeah, so the product will give you, like, if your sparsity is s, then you have s to the log d.
Yeah.
So it is still acceptable in over here, let's say.
Yeah,
Quasi-polynomial is
no,
acceptable.
I'm not sure why this is a counterexample.
Just because here you have all the monomials of degree p minus 1, right? So here,
Yeah, but it's not irreducible.
yeah, it's not irreducible, but
I mean, I think that it's reasonable to ask about the irreducible factors.
the irreducible factors, right? The irreducible factors we don't know. Yeah, that we don't know. That we don't know. But we still have the quasi-polynomial blow up. Yeah, quasi-polynomial we have if we have irreducible, right? Yeah, is that clear? Okay. So, okay, two specific questions. Well, one was the sparsity one that we just discussed, and another one is if P has a small depth circuit, is computed by a circuit of small depth, do its factors have small depth circuits? So that we don't know. And if P has a small formula, do its factors have small formula? That we, well, if you take small just to be polynomial, we don't know. But through standard depth reduction arguments, we have quasi-polynomial blow up for the second bullet. Now, let's just look at the gap of understanding when we just say that the depth is constant, okay? So if P of x, let's say, is a polynomial with s monomials and degree d, so we're in the sparse setting. So this polynomial can be computed by depth 2 circuit, right? So if I apply just Kaltofen and standard depth reduction, then the factors of P of x can be computed by formulas of depth 4 and size exponential in the square root of the degree. So here you notice that even if I give you a sparse polynomial that has a depth 2 circuit, then if I allow you to blow up to depth 4 or even 6, my blow up will be sub-exponential. So the general depth reductions by Agrawal, Vinay, Koiran, and Tavenas, they give a sub-exponential gap. And the main question is, can this be improved? Now, why do we study bounded individual degrees? Well, because I think the simple answer is that we don't know anything in the general case for when the degree is really large. And it's a good generalization of multilinear polynomials. So polynomials with bounded individual degree, they form a very rich class, which generalizes multilinear polynomials, and is also very well studied. So the study of multilinear polynomials started with the works of Ran Raz and Raz Shpilka Yehodayev, giving lower bounds for multilinear polynomials, and then later some PIT. And then recently we have the works of Kumar and Saraf and Kayal and Saha in 2015 studying PIT and lower bounds for polynomials of bounded individual degree.
Bounded means a constant.
Bounded is a constant, exactly. So, but when we look at factoring, the thing is it's trivial to factor when the circuit is multilinear, provided that you have polynomial identity testing, which I won't discuss today. But the factorization is trivial for multilinear circuits. And
So wait, you are talking about, you are assuming like a black box access to polynomial identity testing when you factor?
yes, yeah.
It's not obvious that you have it for all these classes.
No, you don't have it, but let's say if I give you a restricted class, a PIT for, okay, so let me elaborate a bit more. So when I say it's trivial for multilinear polynomials is, if I give you a circuit class that computes multilinear polynomials, and then you can do PIT for this class, so you can test whether a circuit from that class is 0 or not, is computing the 0 polynomial or not, then we can factor easily because the factors are also contained in the class of a multilinear polynomial. Because usually when you have a multilinear polynomial, the factors, they will be in different variables, right? So they usually will belong to the same class. So then it's easy, the factoring problem is easy for multilinear polynomials. But when I come to the bounded individual degree, then little is known. When I allow to mix variables, then little is known. Okay? So, and
I don't see that it's trivial. I don't know if it's
okay.
trivial.
Okay, that trivial. Yeah, so the thing is, usually, if I have a polynomial p, let's say x1, well, x and y, and is multilinear, and it factors, then it's going to be q of x times r of y. And usually,
Which partition it is not necessarily obvious.
right, which partition it is? Okay, yeah.
So
I will say,
I don't know. Okay, you can continue. I'm just a little unhappy with the word trivial.
okay, I'll change the word trivial. Yeah, it's,
I don't see how it goes.
okay. So yeah, it's not necessarily trivial, it's easy in a certain sense. That there is a result that shows that once you have PIT for a certain class, then you can factor just easily for that restricted class.
You are talking about the Saraf Koparty.
No, I'm talking about Shpilka Volkovich 2011, I think. So the
Result.
it's a corollary of us. It's a okay.
It's
It's a piece of a paper. Okay, it's
a piece of a trivial paper.
no, not a trivial. The paper is not trivial at all. No. Okay, I'll change the word trivial. The disregard trivial is a piece of a result of a paper. So so bounded individual degrees is a step towards understanding the general case, because certain problems that we would have in the general case, they don't appear when we have bounded individual degrees. So for example, computing resultants, just for those who know, like computing resultants will be easy in the bounded individual degree, and in general is a very hard thing to do. So at least we have some things that are easy here that allow us to try to understand this class first, and then we can try to understand the general case. Now, this work, what do we show? We show that if P is a polynomial which has individual degrees bounded by R, and it's computed by a circuit or a formula of size S and depth D, then any factor f of this polynomial is also computed either by circuit or formula of size polynomial in n to the r. R is the bound on the individual degree, and the size S, and depth d plus 5. Moreover, this result provides us a randomized algorithm for computing all the factors of P in the time that's the same time as the size of the output. Okay?
So randomized because you use polynomial identity
Yes, randomized because I use polynomial identity testing that I don't have.
So then if it will be, if you have that as a black box,
Then it's deterministic. Yes.
N is the number of variables.
N is the number of variables, yes. Yeah, so the boldface axis, x1 up to xn.
So what is the running time of the usual factoring algorithm for this?
For
Yeah, I mean, you say that you have the factoring algorithm for this kind of polynomial.
yeah, so the running time is polynomial n to the RNS as well.
What you get like the usual.
Oh, so Kalthofen gives you n to the fourth, I think. It's between n to the cube and n to the sixth. It depends on who references and how many variables. But it's usually, yeah. But there you don't get any nice circuit. You just get a very long circuit. So if you don't want to get a nice circuit, then you do it very quickly. But if you want to get a circuit with some structure, then so far this is the only result that we have. Okay, so prior to this work, on bounded individual degrees, there's the result of Dvir, Shpilka, Hodayov, where they say that if P of polynomial x1 up to xn and y is computed by a circuit of size S and depth D, and the degree in y of P is bounded by R, then its factors of the form y minus gx, which I'll call them roots of the polynomial P, they have circuits of depth D plus 3 and size polynomial in n to the R and S. Okay, and now why were they interested in such factors of such roots of the polynomial P? It's because they wanted, in their paper, they wanted to extend the hardness versus randomness approach of Cabanets and Pagliazzo to bounded depth circuits. Because again, Cabanets and Pagliazzo, they use Kalthofen, and therefore you have to work with general circuits. But now if you want to work with bounded depth, then you need to study these factors y minus gx a little bit better. And that's what they do. So they notice that only these factors are important, and they prove this result. That's the main result for them to carry over the approach. And here what we do is we just extend the result to work with any bounded depth polynomial. Okay, so the main ideas of this work. So there's three main ingredients that enter in this proof. An outline of how to put things together. So we're going to describe lifting, and then we're going to go on to root approximation and the reversal. And we'll begin now with the lifting, which is ubiquitous everywhere. So now, suppose that our input P x, y is equal to y minus g1 times y minus g2 of x. So it factors completely into roots. That's really nice. And it's also monic, right? So we have these two very nice things. It factors into linear factors, and it's monic. And suppose, furthermore, that the restrictions of g1 and g2 to 0, they are different. So mu1 is different than mu2. Okay, we can get that by, as long as the polynomials are different, we can get it if we have black box access to PIT. So let's assume that this is happening. Now, how do we factor in this case? So one idea is to try to build the polynomials gi, g1 and g2, by building the homogeneous parts of g1 one at a time. So we first find mu1, and then we find the linear parts of g1, and so on and so forth. Okay? All right, so notice that if I restrict to 0, I get a univariate polynomial, which we know how to factor. So then we found the constant terms of the roots. But now, how do we find the linear terms? Well, notice that if I set now y equals to mu1 in the input polynomial, I get p of x mu1, which is equal to mu1 minus g1 times mu1 minus g2. But now, since mu1 is different than mu2, the constant term of the second of mu1 minus g2 is non-zero. But the constant term of mu1 minus g1 is 0. Here is a polynomial that does not have any constant terms. But moreover, the linear part of this polynomial is equal to the linear part of this polynomial multiplied by some constant, which we know because we know the first roots. Yeah? Okay, so we can recover the linear term of g1 but just with black box access to the polynomial p. And that's what we do. So if we proceeded in this way, then we can recover the roots and factor the input polynomial, right? We're going to build it one at a time. And that's what Virch-Pirka-Yehudayov did. And they just showed that you can actually compress the circuit because you have bounded individual degrees. So this technique is called Hansel lifting or Newton iteration, and is pervasive in all the factoring algorithms, such as Zasenhaus, Kalthoff, and Virch-Pirka-Yehudayov, and many other ones that came after Zasenhaus. So again, just restating Virch-Pirka-Yehudayov, we'll use this as a black box, that we can get the roots with depth d plus 3 and the size. Okay, so this is lifting. Now, if we're to extend this approach, there are two main issues. The first one is, well, what if P does not factor into linear factors? What do we do in this case? Well, in this case, we're just going to extend the results of the Virch-Pirka-Yehudayov to work with, we're going to approximate the roots in the algebraic closure with low degree polynomials in f of x. Pretty much, if you want to think of it as in a simple way, we're just going to look at the Taylor expansion of the roots, and we're going to work with them instead of the exact roots. The roots don't need to be exact. But what if P of xy is not monic in y? Well, then we're going to use reversal to try to reduce, to try to induct on the number of variables. Reverse I'll define, it's very simple. To reduce the number of variables and try to make the polynomial monic. Okay, so we want to reduce to that case. That's monic, but not necessarily has linear factors. Okay, so let's describe the root approximation now. Yeah?
Can I take you?
Of course.
Sorry.
More?
Yeah.
Here?
Yeah, here. Yeah. So you said that okay, you get the linear part of G2.
I get the let's say that I get the linear part of G1. Yes.
G1. But how do you do it? Like you can read the polynomial, and what do you?
Yeah, good. So what I can do is so I know that this polynomial here, the lowest degree part of this polynomial, so the constant is 0, and the linear part is exactly a multiple of what I want, constant that's multiplying. So how do I recover, right? That's his question. Okay, the way we do it is by, you can just do polynomial interpolation, and then you can recover the degree 1 part of P. Yeah, usually that's how we do. We're gonna find, yeah, so if I have, so the task is, if I give you black box access to P, recover the homogeneous part of degree K, and that we can do efficiently. Yeah. So okay. Actually, I mean, let me just show, oops. Okay, I can just show you a little bit like in the board, like if you want to know. It's very simple. The idea is, let's say if I have one variable only, it's sum of ai y to the I. What you do is, well, you have P of y, P of t times y, well, P of 2 times I, P of 3 times y, and so on and so forth. Or sorry, if the polynomial is this way, you just compute P of 1, P of 2, P of 3, and so on and so forth. And then you just have linear combinations of the coefficients. Right? So then you pick this vector, and notice that this vector is just the van der Monde matrix times the coefficients, A0 up to AR. Now the only thing is van der Monde matrix, right, which you can always do. So this we do with interpolation, and notice that the AIs can lie in any ring. And in this case, the way we recover is exactly by setting the AIs as the polynomials, right? So if you want the linear part, you just invert a van der Monde matrix. Does that make sense? Okay, so that's pretty simple, and that's what we do to recover given black box access. And then you interpolate because you have the degrees. Well, if you're given black box access, sorry, let me clarify. If you're given black box access, you can only give back black box access. So I'll just give you exactly, through the circuit, I'll give you something that exactly computes just the linear part.
With higher degree, the van der Monde matrix doesn't
It just goes up to, no, it goes up to the degree of the polynomial. Yeah, so it will grow up to polynomial.
To the total.
Total degree, yeah, but it's polynomial, so you just have a combination of polynomially many things. So the van der Monde matrix, the size of the van der Monde matrix is the degree to which you want to interpolate.
Oh, if it's a multivariate polynomial,
Mm-hmm.
what will be the size of the van der Monde matrix?
It will be,
N to the d if
it will be the degree. So okay, so if I want to do interpolation, okay, so if I want to do interpolation with many variables,
you have n variables in each degree, if we have 2d, then you need n to the d, right? Because they are n to the d coefficient.
oh, good. So that's a good question. No, so the interpolation we want to do is the following. Suppose now, okay, so
In general polynomial, or certainly it's d to the n, that's not good.
yeah, so that's not good. So what we're gonna do is the following.
No, it's doing more efficient, no?
Okay, so maybe I did. That's a very good question. So let me. So you understood how we do it with one variable only, right? Now, what we just do is suppose that you have you want to recover just the homogeneous part of the polynomial of a certain degree. So now instead of having just y, I have y bar, which is sum of ai, and then here instead of putting, well, is all the polynomials is the homogeneous part of degree I that I'll denote by pi of y. Right, so you can write this polynomial p of y by just grouping all the homogeneous parts of degree I. And then now I can use the same van der Monde matrix. So let's say that this polynomial has degree d. I can use the same van der Monde matrix to do p of y, p of 2y, 2 times y, p of, so I multiply each.
The point is that you are not recovering individual coefficients, you are just recovering together
Right.
the whole homogeneous,
Every homogeneous component.
You don't write it down, it's just, you get it by a reduction to the black box access to the polynomial.
Exactly. So the point is, the point is that I'm not recovering each coefficient. I guess that is right. I'm not recovering each coefficient. I'm giving you the whole homogeneous part at once. And if I can, and through that I can just use a van der Monde matrix.
So you get circuits to these homogeneous parts, some of which gates are just gates evaluating the original polynomial.
Right. Yeah. Okay. So now, so now let's go back to the root approximation, right? So now suppose that our input is a general degree R polynomial in Y, and it's monic, but does not factor into linear factors. Now, if P in xy is equal to f times q, where f is going to be monic because it's a factor of P, is irreducible and does not divide q, suppose they were in the setup, which we can make it happen, but let's not worry about it. Suppose they were in the setup. Now, notice that any polynomial factors completely in the algebraic closure. So if we factor P in the algebraic closure, because f is a factor, we have that some of the roots of P will be roots of f as well. So all the roots of f are roots of P, which means that if I have only access to P, I can still try to recover the roots of f by having access to P. So now we don't need to worry about the algebraic closure because we're not going to use it, right? We're going to approximate the roots by low degree polynomials, but this is just to simplify what we want to do, right? We want to find the roots of f. So now, since P and f, they will share roots, then we can try to approximate the roots of P and f by polynomials git of degree t, such that the polynomial fx git of x has only terms of degree higher than t. So it's the algebraic analog of doing Taylor expansion, right? We have that we're approximating the roots up to degree t. So let's just have this definition now. From now on, we say that f and g are equal up to degree t if the polynomial f and f minus g only has terms of degree higher than t. So if they agree in the low degree parts, okay? So suppose that we can find these roots, okay? These approximations. Suppose that there is these polynomials of low degree that approximate the root such that f of x git of x is equal to 0 up to degree t. Suppose that we can do that. Then we can prove the following lemma. These polynomials, these approximations to the roots, they are such that f of x is equal up to degree t to the product of y minus the approximation of the roots. So the approximation of the roots can also approximate the whole polynomial. Okay, so we can convert the approximation to the roots of f to actual approximations to the whole polynomial.
Is it just from the definition, or there's something else going on? Is it just by definition? I mean, the fact that this implies this lemma is more or less the definition. We're working in the ring where x to the t plus 1 is 0. Right?
Where x to the t plus 1 is 0.
You forget about.
Right. Yeah.
You mod out by all high degree polynomials.
Right, exactly.
So
Yeah, you just need something. Yeah, it's not by definition. You have to do something, which I'll do now.
okay, you do it.
Yeah, but it's not that complicated. Yeah. So what we do is, well, the basic idea of the proof, it follows by Euclidean division, right? That's what you were saying. So what Avi said is that this follows by Euclidean division. So how do we do this? If we divide f, so we know that f, we found all the roots, g1 up to gk. And now let's do Euclidean division of fxy by y minus g1t. So what happens is f is equal to some polynomial f1 times the root plus the remainder, which is exactly f of x g1t of x. Now what we need to notice is that the degree of this polynomial f1 is k minus 1 in y, and this is equal to 0 up to degree t. And then we have the up to degree t, it factors. Right? The approximation of the root is actually a root. And then we can continue, and if we look at f x g2 now at the second root, is going to be equal to f1 of x g2 times the difference between the roots up to degree t, right? Just because of this equation, I can just substitute. So, but now what do we need to notice? Notice that this is equal to 0 up to degree t, because g2 is also not a root of f, it's a different root of f. But moreover, we needed the conditions that the roots are different to say that this has a non-zero constant term. And therefore, this implies that f1, that g2 is also root of f1. So now, if we divide f1 by the second root, by y minus g2, then we get the same thing, is equal to 0 mod t. So we have the f1 is equal to some other polynomial f2 times y minus g2 up to degree t, and so on and so forth. So by induction, we can complete the proof. Now, how do we obtain these polynomials gi? Because if you obtain them, then we should be done in this case. Well, since each root of f is also root of p, we can obtain the gi from p via lifting that I showed you before. Right? So if we look at our parameters now, we have that f is equal up to degree t to the product of the roots. And, well, each root by Dvir-Shpilka-Erdős, by some extension of Dvir-Shpilka-Erdős, we can obtain with the same parameters, depth d plus 3 and the size poly n to the r and s. So this circuit now has depth d plus 4 and the same size, poly n to the r and s. So now, I just want to recover the low degree parts of this polynomial that we have a circuit for. And then we do exactly that black box reduction that we just discussed. We just do interpolation, and we get a polynomial. We get a circuit of depth d plus 5 and the same size that computes f.
So t will increase. You start with t equals 1, 2, 3.
Yeah, t will increase, right? I start with, yeah. But t can only go up to r times n, right? So we don't care much about it. Okay, now there's an observation here that for the general case, we need to keep this product fan in. We cannot compute f exactly because, well, you'll see why in a little bit. So just keep in mind that we cannot find the approximation, then compute the right polynomial, and then keep it going, because this will increase the depth. And this will be clear in the next part. So now let's talk about reversal. So the setup now is, suppose that our input is the complete polynomial. Now, it's the most general case, where the constant term p0 of x and the highest degree term, the leading term pr of x, they're different from 0. Now, again, let p equals to f times q, where f is, again, a sum of fi times 2yi, is irreducible and does not divide q. Again, it's easy to get to this condition. So let's just assume that. And the game plan now is the following. We need to reduce the demonic case because we spent 40 minutes talking about it. So how do we do it? We just look at p equals to the leading coefficient times this rational function, and also f times its leading coefficient times this rational function. And the plan is we recover fk, the leading coefficient of f, leading coefficient of p, by some induction, and then we recover the part of f that depends on y from the part of p that depends on y. Okay? So, and let's suppose that we can do that. Let's just look at the naive recursion to see where do we have a problem here. Well, we have our setup. Now let t of Sn be an upper bound on the following thing. Suppose that f is a factor, and there exists a circuit phi that approximates f such that the depth of phi is d plus 4. Its size is bounded by this quantity t of Sn, and the top fan in is a product gate.
You want to show that the depth does not increase in this iteration, right?
I want to show that the size does not increase, right? The size.
The
The depth I'm maintaining d plus 4, and I'm requiring.
You're using only the original circuit, not what you constructed.
Exactly. I only keep using the original circuit. Right. So the idea is let t of Sn be the upper bound on all of the circuits of depth d plus 4 and have top and in product gate such that these circuits, they approximate any factor of p. Okay? So given this bound, our recursion will be the following. So t of Sn is less than or equal than the quantity on the right, t of 3r times s and n minus 1 plus poly n to the r and s. Where does this recurrence come from? Well, here is the recursion that we have, right? Inductively, this is what we pay to recover the leading coefficient of f from the leading coefficient of p. And notice that this 3rs comes exactly from the fact that I need to perform this interpolation to obtain the leading coefficient p of r. So here, the size of the circuit computing p of r is bigger than the size of the circuit computing p. And that's the best that we currently know how to do. We don't know anything better than that. So, and the other term is the size of the part depending on r. So far, just think that we're going to extend the Wierspiegeldajow to work also with rational functions. Okay? But now, if we follow our recursion after t steps, the recursion becomes really bad. Because every time that I decrease one variable, I multiply by 3r on the size of the circuit. Right? So then this is exponential when t is roughly the number of variables. So this is pretty bad. We cannot do the recursion this way. Now, how do we avoid the exponential growth? Well, it's hard to get the leading coefficient from pxy. But it's easy to get p0, the constant term, from the circuit computing pxy. Why? Well, because p0 is just a restriction of p. So, moreover, p0 has smaller circuit size than p. So what we do is, what if we could make p0 the leading coefficient? Then we're in good shape. And that's exactly what we're going to do, and that's the definition of reversal. And here's the definition by example, right? If p is a polynomial of degree 5, p5 times y5 plus p4 times y4 plus p0, then its reversal is what? I just pick all of the coefficients and I reverse them. So in this case, I'm going to have p0 times y to the 5, and then the other ones are 0, plus p4 times y and p5. So now I'm putting the simple coefficients at first. So the reversal can be efficiently computed from the circuit, computing the original polynomial. Why? Because I can do the similar kind of interpolation just to shift the circuit size. That's the order of the coefficients. So this technique was used as well for factoring univariate polynomials, and we extended to work it.
So it's more or less like substituting 1 over y for y, or
Yeah, you can do 1 over y and multiply by y to the r. Right. Yeah. So now, the recursion with the reversal, how does it look like? Well, now, if we take the reversal to compute the factors, then our recursion becomes Tsn less than or equal to, now look, we avoid the blow up here on the recursion, and we shift the blow up a little bit to the poly aspect of it, because now we use the recursion, the reversed polynomial has a circuit of a little bit of a larger size, but it doesn't matter because that's the additive part of the recurrence. So here's what we recover f of 0 from p0, and the other part is the size of the part depending from y. But the blow up there doesn't matter because that's additive, right? That doesn't enter the recurrence. So after t steps, our recursion remains of this form. So this is what we want. Okay. Now, so this is the reversal. And now let me just touch a little bit on how do we work with rational functions, right? Which is also is a technique from Strassen, that how do we adapt the root approximation to work with rational functions? Because now we can say, well, it's a polynomial that has degree up to degree, that has only terms of degree higher than t. So here we notice that if p of xy is of the following form, one is a polynomial 1 minus qx, where q does not have any constant terms, plus the other polynomials, and if I look at this polynomial r of x that does not depend on y, then, well, up to degree t, I can transform this polynomial, p times r, into a monic polynomial. So it's a monic polynomial, which is really what we liked, because we looked at we know how to approximate roots of monic polynomials. And this is equivalent to the rational function that I showed you back then, because this is equivalent to dividing by 1 minus qx, mod x to the t, like Avi was saying. So, well, so then this is just to show that any root of p, if g is a root of p up to degree t, then it remains a root of this polynomial, because r is a constant, mod y, if I only look at the variables y. So I can use this as the monic polynomial, which is that part depend on y. So I can use all of the things that I defined.
So is there a general Strassen's removal of division from circuits computing polynomials? It does not increase the depth at all, right? Or it does increase?
So,
Maybe it doesn't.
well, you will increase the depth just by 1. So, but Strassen does a different way of.
Yes, so I'm asking, I mean,
Uh-huh.
it's not related to what you do, I'm just wondering.
So he increases the depth because you have to look at this expression, right? So, okay, so Avi has a question. So Strassen has a trick that you can eliminate divisions from any computation.
This is a trick.
This is the trick.
This is a trick.
Yeah, this is his trick.
You write 1 over q.
Right. So.
As an expansion, but up to the degree of any polynomial that will ever be computed in the circuit, and then you can forget about the rest.
Exactly. So he increases the depth because in the end, you have to compute this polynomial r of x. And q will have the same depth as your original circuit. And then, but this has depth higher than your original circuit, because you need at least the depth d plus log t to compute this. So yeah, you increase the depth there in Strassen's trick. So why don't I need it? Because I'm not, even though because I'm not accessing, I'm going to use p of xy.
Yeah, so you're just because it's a reduction.
Just because it's a reduction.
One reduction that's from
Exactly.
computing this polynomial to computing.
Yeah, exactly. So, okay, so just to, so Avi was asking, well, if I'm using this polynomial r of x, and this polynomial has a depth higher than the depth of p, why doesn't this blow up actually enter in my analysis? And the reason is because I'm not actually computing this r of x. I'm just using the r of x for my analysis. I'm just using the r of x to compute the roots, but I'm still going to do everything by accessing p of xy. So I only use access to the polynomial p. That's why my depth doesn't blow up by this.
So actually,
No, it's not.
How you get Q from P?
Yeah, no, it's not. It's a bit technical, so I wanted to. I can talk to you maybe offline about this. Yeah. So.
Just pointing that it's an issue.
Yeah, this is an issue. Yeah, there's an issue. It has to be dealt with and makes expression looks a little bit bigger and longer. So okay. So now we dealt with the reversal. Now let's see how all these three ingredients come together. So if I have my input P and I want to find the factor, the irreducible factor F, the first thing that I do is I compute the reversal of P, and I just observe that the reversal of P, that I'll call P tilde, is equal to F tilde, which is the reversal of F, times the reversal of Q. That's simple to see. And now the size of P tilde becomes 9r squared times S, which is okay, because R is a constant. And the depth remains D. And I'm assuming here that the top gate of P is an addition gate, which I can assume just for simplicity. Okay, so then now what I do is I write P tilde as it's equal. Notice that P tilde is equal up to degree T to P0 of X times some monic polynomial in Y, gxy. By what I just showed you in this slide, so this G will be P tilde times this polynomial R of X. Right? So you can think of it as a rational function. Let's just think of a rational function to simplify things. And F tilde of X, the same way, will be equal to F0 times some little g of xy, which is also monic in Y. Now, each approximate root of this, so we have the little g and the capital G. Now notice that each approximate root of little g is also an approximate root of capital G. So then I can, if I find the approximate roots of little g from the axis that I have to capital Gxy, then we know that g of little g of xy is equal up to degree T to the product of the approximation of the roots. Now, we know that this has depth d plus 3 and the size poly s n to the r, and the top gate is an addition gate. This is just by extending the Virch-Pirker-Hadaoff. And then now, this circuit has depth d plus 4, the same, I'm just multiplying a constant number of them, and the top gate is a product gate. But by induction, we have that f0 of x is equal up to degree T to some other polynomial hx that can be computed by a circuit with size poly s n to the r, depth d plus 4, and the top gate is a product gate. That's why I wanted to maintain the product gate as the top. So now, when I multiply both of them, what I get a circuit that still has depth d plus 4 because the top gate was a product gate, and the size remains the same. And then, therefore, now I have an approximation to my factor, to my general factor, and I can recover it by just doing the interpolation. And the interpolation given by this Vandermonde matrix is just a linear combination of the axis of the polynomial. So I get this bound. I get the blow up and the depth is just an addition of 1. So this is how we obtain the factors.
Well, the bound, why was it critical to get a bound on the individual degrees? Because when you are computing the factors, you keep...
Right, yeah, so the bound on the, so I was asking, when is it crucial to get the bound on the individual degree? The crucial bound on the individual degree is actually only coming from the Virch-Pirker-Hadaoff extension. It's only because to obtain this y minus git, I need the bound on the individual degree. That's where I use the bound there. And that's why the size also is poly s to n to the r.
So why is it again n to the r? It's just because of their result.
Just because of the result.
Yeah, but is it obvious that it cannot be replaced with n times r?
No, it's not obvious that it can be replaced by n to the poly r, but you have to just understand, I think to that you need a clever depth reduction of the recurrence that they use. So if you just want to use Dvir-Shpilker-Hdayoff, if you want to extend them in a somewhat black box way, then this is what you get. But yeah, nothing is clear. It's open, and it's actually an open question. Whether, yeah. So the blow up actually just comes from finding the roots. The poly S n to the r actually just comes because it's really, so far we don't know how to find the roots efficiently. So now, let's just recap what we have done. So we showed here that if P is a polynomial with individual degrees bounded by r and has a small low depth circuit or formula, then any factor of P is also computed by a small low depth circuit or formula, small polynomial. I'm remaining on the polynomial regime. Furthermore, we have a randomized algorithm that runs on the size, in time of the size of the output, linear on the size of the output.
So the randomized algorithm is because of the black box, or because of the Dvir-Shpilker-Hdayoff, or?
Yeah, so it's because of the black box, it's because of the PIT.
Because of,
Right, it's because, yeah, because all the reductions are, yeah, so the only problem to get the to get randomized is because we need to hit a resultant of the coefficients of P, and yeah, we just need to hit that resultant exactly, so that I can make all those assumptions that, for example, the leading coefficient also is one, it has a constant term and all these things. So all these nice assumptions that I'm making, I need to have PIT for them. But once you give me that, then everything is deterministic.
But actually, you probably need also some randomized shift of the variables independent of
Yes.
PIT, just to get these coefficients, constant coefficients to be different.
Exactly. Yeah. So
that's not PIT.
yeah, if I hit the resultant, I can guarantee all of this. That's where.
Yeah, sure.
Yeah. There's a discriminant actually. Yeah.
Yeah, well, PIT is, it depends what you call PIT. If PIT is a hitting set, then it's fine.
Yes.
But if PIT is just a procedure that tells you whether it's zero or not, then it's not.
No, it is as well, because
Yeah,
if you hit the resultant, then you can find yeah. So yeah, so I think the question that Noga and Avi asked is, well, where is the randomness coming from? It actually comes in two places. Well, one, it comes in the setup, because I need to assume that the leading coefficient has a non-zero constant term, and I also need to assume things about the roots, and that involves hitting some certain polynomial, proving this, finding a non-zero assignment to a certain polynomial, and also in the end I need to do a testing to test if the factor that I actually found is an actual factor of my polynomial, and for that I also need another PIT. So I use randomness there. So now, moreover, besides this theorem, we have a general framework here that is the following. So in the survey by Shpilker and Hdayoff in arithmetic circuits, they asked whether the factors of low depth circuits have polynomial sized circuits of low depth without the bounded degrees restriction. And what we show here is that what Avi pointed out in the previous session is that, and the question is open even for factors of the form y minus gx, so for roots. And what we show here is that if P is a polynomial computed by a low depth circuit and all its approximate roots are also computed by small low depth circuits, then any factor is computed by small low depth circuits. So the problem that Shpilker-Hdayoff asked, to settle this above conjecture that they have, it's only enough to solve the question above for approximate roots instead of just finding the actual root factors. But I think even if you can show that these factors have poly-size and low depth circuits, then you can easily extend to approximate roots. So what this work shows as well is that to settle this above conjecture, it's enough to work on the question for the roots, to show that the roots have simple circuits.
And approximate is up to some polynomial, T is some polynomial in n times r.
Right.
T is the degree of
Yeah, T is the degree, the maximum degree. Yeah, T will be a polynomial as well, right? So approximate roots to the polynomial degree. And usually when we work with arithmetic circuits, it's assumed that P, the degree of P is polynomial. So now there's lots of open questions remaining from this work, which is one, the main one is to remove the exponential dependence on the degree for roots. Another one is reduce the depth bounds in the work of De Vries, Spieker, Hidayov. So for example, can we show that factors of sparse polynomials have small depth 4 circuits? Remember that the gap that I showed to you was a sub-exponential gap, right? And moreover, on the de-randomization part is, can we de-randomize polynomial factorization, even for bounded individual degree polynomials? So currently, this question is open even for sparse polynomials with bounded individual degrees. We do not know how to factor deterministically sparse polynomials with bounded individual degrees. So that's all.
Questions?
So the hopeful way to de-randomize it without de-randomizing PIT, right?
Yes.
No. It's at least factoring is at least a part of it. You cannot.
So
Yeah, so I think Noga's question is if we cannot de-randomize PIT in the general case, if we only have restricted PIT, the hope is to use the restricted PIT to say yes to factor.
That was also the DSY motivation.
Right, DSY motivation was the same thing. So the DSY, they wanted to, yeah, because our understanding of bounded depth is increasing. So maybe with the PITs that we have, they're somewhat weak, we can still get some non-trivial results with those. We don't need the general.
Yeah, but we don't even have PITs for these classes.
Yeah, we don't have even PIT that hits circuits is strong enough to de-randomize sparse polynomials. So that's lots to do.
So I have a question about the related thing. You started with sparse.
Mm-hmm.
Mentioning sparse. What's the status of just factoring into sparse? Taking a sparse polynomial, what's the size of the sparse? It's just quasi-polynomial. Is an upper bound?
No, we don't know any upper bounds. We know that it's at least that much because of the construction.
Quasi-polynomial, sorry, that example.
Yeah.
We don't have upper bounds.
We don't have any upper
Even
bounds.
existentially,
No, even sub-exponential, yeah, we don't have any bounds at all. Yes.
Just so that I understand the question.
Uh-huh.
It's not, if you take a polynomial in fp of x,
No, not of fx, many variables.
Many.
let's say in one variable, I'm still trying to understand
Yeah.
one variable.
Uh-huh.
Simple math. If it's sparse, you don't know if the irreducible factors are sparse.
Yeah, okay.
Now it will not.
So
In one variable, you know it will not, because the x to the p minus 1 that's a two monomial factors into x minus 1 times something with n. Yeah, right. So n is unbounded. So even in one variable, the sparsity grows with the degree. Even if you start with a polynomial of just two monomials.
Yeah, so
But the factors are linear. Is that called sparse or not?
okay, so good. So that's okay. So let's.
Things count in monomials. That's the meaning of sparse.
But each factor is just two monomials.
Yeah. So okay. So maybe let me just write it here. So suppose that you're in the rational numbers, let's say, and now I give you the following polynomial: x to the d minus 1. Now all the irreducible factors of this polynomial. Well, you're gonna have one that's x to the d minus 1 plus x to the d minus 2 up to 1. This is irreducible.
D is prime, yeah.
If d is prime, yes. Let's say that, yeah. Okay, p.
This is over the rationals.
This is over the rationals, right. But then this already shows that the blow up is from 2 to 2 to the log of the degree. I don't know if you can see, but it's 2 to the log of the degree. But if you want to say, okay, now what about complex numbers? And if I give you more variables, because now the situation becomes a little more interesting, right? But then we can scale this situation for the complex numbers by just picking the polynomial x1 to the p minus 1 times x2 to the p minus 1 times xn to the p minus 1. And then if we take the product of these guys here, xi So this, and you can say justifiable so that they're not irreducible. But I can modify this very easily to make it irreducible. I can just add p plus this. Now this becomes an irreducible polynomial that divides this polynomial. Well, I have to add now p times x1 minus 1, xn minus 1. So this polynomial has 2 to the n plus 1 coefficients, but it has an irreducible factor with p to the n plus 1. So the bound still remains dependent on the degree. Does that make sense now?
So if p equals n, you have a polynomial with n monomial, n squared monomial, then its factors have some like n to the log n.
Yeah, so you still have the, so the gap here is quasi-polynomial, right? So if this is s to the log n. So that's a lower bound that we have. We know it can be at least this much, but we don't know if there is a polynomial that has an irreducible factor that is exponential, that has exponentially many terms. That's the question.
Maybe it was not stressed enough in the beginning. I don't know if you knew it, but I think it's an amazing fact that every mathematician should know. If you have a polynomial given to you by a formula, multivariate, so it can describe determinant of it, right? The irreducible factors of this polynomial all have small formula.
Yeah, this is.
Yes, it's so amazing, and the question is whether then the analog, if you replace small formula by small.
Yeah, exactly. That's the.
All right, thanks.
Yeah, thank you.